We've got to talk about conventions in the capacitor world. There are some important conventions, but these conventions make life a lot simpler for us. For example, for delta V between the plates, when you have two plates, there's going to be an electric field between them, and that means there's going to be a potential difference between them. But the great news is for the capacitor chapter is that delta V, we just use the absolute value. For charge, you just use the absolute value of charge. You don't have to worry, negative or positive. You just call it positive Q, and that is the charge on one plate. Now, why is that the charge on one plate instead of both plates? If you understand what a capacitor is like, what's the net charge on the entire capacitor? Let's go back to our picture right here. What's the net charge on combining both plates? The net charge on our entire capacitor is just, you guessed it, 0. A capacitor, it's often said, holds charge, but really what it's holding is energy, because the net charge on my capacitor is always 0, but there may be up to 5 coulombs on each plate of this thing. That's totally possible. I've told you before, it's really, really hard to get a coulomb all in one spot. But if you have a coulomb, a positive coulomb, right next to a negative coulomb, that's still stable. So now we have our definition of capacitance. Caps are quite overvalued. Incredibly useful mnemonic. So caps are quite overvalued. The capacitance definition is the ratio between the charge on one plate and the voltage difference between the plates. And for our conventions, Q is always positive. This is the absolute value of Q. And delta V is always positive because we're always using the absolute value of delta V. So everything's positive. It's easy. Capacitance can only be positive. For this equation, C is the capacitance in farads, named after Michael Faraday, so it does have a capital F. Q is the charge magnitude on one of the plates, and of course on the other plate will be negative Q. And the delta V is the potential difference from one plate to another. That is the definition of capacitance. Now, what happens to the capacitance when you triple the charge on one plate of the capacitor? This is actually where this equation can be quite misleading. Here's a typical capacitor. Maybe it's a little bit larger than typical, but you can see right here, it's marked with its magnitude 1 farad, 1.0 F. What happens to the capacitance of this thing when I triple the amount of charge on there? Well, I'll give you a hint. They're not going to change this label every time I charge this thing up. What happens to the capacitance? Nothing. Nothing happens to the capacitance. What happens is delta V will increase. When you put triple the amount of charge on it, delta V will be increased by 3 times. So capacitance depends only on geometry and materials. This is so very important right here. It only depends on geometry and materials. It does not depend on Q nor delta V. Capacitance depends entirely on the size of the plates and what's in between the plates and what shape the plates are. So capacitance is a measure of how much charge can be held on each plate per volt between the two plates. 1 farad is defined as 1 coulomb per volt. So for example, my 1 farad capacitor right here can hold 1 coulomb of charge on a plate if there's a 1 volt difference across it. Or 5 coulombs, it can hold 5 coulombs on one plate if there's how much difference across it. How much voltage would I have to put from there to there using batteries or my Genicon generator? How much voltage would I have to put across this to hold 5 coulombs on one plate? Well, the capacitance is not going to change. This is going to be a 1 farad capacitor. I don't know if you can read that, but it'll be 1 farad no matter what you do to it. How much voltage would I have to put across it to hold 5 coulombs? Well, that would just be 5 volts across it. Will hold 5 coulombs on one plate. Again, net charge on this thing is 0. Now, caps, this 1 farad capacitor is actually a relatively large capacitor. They're typically rated in microfarads. And really, I misspelled this. This should be a lowercase f when you're actually doing this. But on WebAssign you'll have to write it like this if you want microfarads. But the correct way to spell it is with a lowercase f there. Mu f is microfarads, picofarads, pf, or in the case of capacitors used in computer memory like DRAM, dynamic random access memory, those are in femtofarads. And let's see if we can remember what those prefixes mean. A picofarad is 10 to the negative 12 farads. A femtofarad, and what's good is that the commonly used ones are always in like kind of steps of 3. A femtofarad is 1 times 10 to the negative 15 farads. And that's how tiny those teeny tiny capacitors are inside your cell phone or your smartphone when you're doing dynamic random access memory use. For example, anytime you're using a program, those little tiny capacitors, each of which hold 1 bit, like a 1 or a 0, those are in femtofarads, like between 20 and 30 femtofarads.